Well, first of all, in order for a function to have an inverse, it has to be what's called a one-to-one function. And we'll talk about that for one thing. When you hear inverse, think of the opposite. Okay. An inverse function must be a one-to-one function. And you'll find later on I'm going to write it 1-1 instead of writing it out. But an inverse function must be a one-to-one function. So we need to talk about what does it mean to be a one-to-one function? What has to take place if it's a one-to-one function? Well, if it's one-to-one, it's got to be everything that was with the function. Remember on functions we did a while back, on a function your x's couldn't be repeated. It had to pass the vertical line test. There couldn't be any y squares or y's in absolute values, right? It had to be just one x on all of them. Well, if it's one-to-one, there can only be one x and one y. They can only correspond, each x has to correspond to exactly one y value. So if it's a one-to-one function, the x's and the y's cannot be repeated. Step 2, it has to pass the vertical and horizontal line test. Now the horizontal line test is just like the vertical. Remember the vertical line test is if you draw a vertical line anywhere through your graph, if it passed through more than one point, it was not a function. Well, the horizontal line test is if you draw a horizontal line anywhere through your graph, that it will not, and it passes through more than one point, it will not be a one-to-one function. But one-to-one functions have to be functions as well. Step 3, put it over here. Step 3, you cannot have a y to an even power. You cannot have an x to an even power. You cannot have y inside of absolute values or x's inside of absolute values or inequalities. So it's everything like we did with the functions that was all based on none of the x's being repeated, except now we've got to take into account all these things with the y's too. So the y's can't be repeated. It's got to pass the horizontal line test, which that makes sure your y's aren't repeated. And then you can't have x's or y, no even exponents basically, no absolute values, and of course no inequalities, which is your less thans, greater thans, and all those sorts of things. So we're going to kind of do like we did on that the test 3, where I asked you if it was a function, yes or no, those types of things. We're going to do the same things with one-to-one. So I'm going to ask you, are the following one-to-one? First, we'll start out with graphs. I got this over here, copy. one-to-one function? Yes, no matter where you draw, it's a line, and no matter where you draw a vertical line or horizontal, it would only pass through at one time, right? Vertical passes through it once, no matter where you draw a horizontal, it would only go through at most one point. What about number 2? Would it pass the vertical and horizontal line test? Yeah. Yes. What kind of function is this based on your basic functions? It looks like which one? It looks like a square root function, so keep that in mind. What about number 3? Would number 3 be a one-to-one function? No, because it fails the horizontal line test. It passes the vertical, but fails the horizontal. What kind of graph is that? The parabola, which is a quadratic. It's got an x squared, right? So we're saying x squared graphs, like what you did in the last test, always make a U shape, which would always fail the vertical line test, right? Let's look at number 4. What do you think about it? Vertical line test, it passes. Horizontal, it would pass. Do you agree that this graph looks like half a parabola? Do you agree? And that's going to be important to us in a minute because we see that the graph over here you told me that looked like a square root graph. It is a one-to-one function, which means it would have an inverse. But what's the opposite of taking the square root of something? Squared, right? But we just said a squared graph is not one-to-one, which means it wouldn't be an inverse. We're going to find out in a little bit if you can restrict your domain where it would actually be an inverse, which is what we're going to see here. What about number 5? No, it fails the vertical line test, right? So it's not one-to-one. So are we good on looking at the graphs and telling them it's a one-to-one function? All right, next let's look at some equations. Number 6. These are still yes or no. Let's look at these. What?
Now go 6, 8, 9, 10. So we get it.
Okay, hold on. You know what I mean. Let's look at these examples. Okay. Okay, we're good. Now we're good. Are we ready to answer yes or no? Now remember, it's not a one-to-one function if you've got even exponents or absolute values or inequalities. Otherwise, your answer is yes. So in number 6, would it be yes or no?
Yes.
Yes, there's no even exponents, no absolute values, so you're good. What about number 7?
No. Oh, I'm looking at it. Nice.
This 7. This would be yes, right? If you were going to think about the exponent on that x, it would be, say, a 1/2. You know, fractions aren't even or odd. One's odd, two's even, so it's neither one. What about 8? No, because what's that exponent on that x?
Square, just even.
Right, so your answer is no. It would not be 1-to-1. What about 9?
No.
No, you got 2 even even exponents, right? What about 10? Yes, no even exponents, no absolute values. What about 11? No, you got that even exponent. What about 12? No, you got an even exponent. What about 13? No. Good. So is everybody okay? Tell them it's a one-to-one function. Now we're going to talk about the definition of the inverse function. In order for it to have an inverse, it must be one-to-one. So now we're going to prove that things are inverses, and we're going to learn how to find the inverse. Alright, by definition, you're told that that f of x and g of x are inverses if and only if f composed of g of x equals x and g composed of f of x equals x. So you got to use that composite function that we did back on test 3 again, that function test. And the good thing about all this stuff coming up is the fact that it's going to review you. When you get ready to start showing your exam, you're going to have done these composite functions again, so you're going to remember them. So if two functions are inverses of each other, they're composite functions when you put the g function into the f, or the f function into the g, they both must equal x in order for them to be an inverse of each other. Okay, so let's look at an example. Your directions are the following inverses of each other. And you're going to prove by the definition. So number 1, let's say if we have y is equal to 3x plus 2, or f of x is equal to 3x plus 2, and g of x is equal to x minus 2 over 3. Well, let's think. I told you earlier, inverses are opposite. So let's look at the first one. What's the opposite of multiplying by 3? Dividing by 3. What's the opposite of adding 2? Subtracting. So you look at this and you think it kind of looks like an opposite. So you would think maybe the answer is going to be yes. But you're going to have to prove it, because sometimes it can be deceiving. So first of all, we want to find f composed of g of x. Remember, that means you put your g of x function inside of the f function. So that means in f, you're going to, everywhere there's an x, you've got to put x minus 2 over 3 in its place. Here's my x in this function. So right there where there's an x, you've got to put your g function. So that means you're going to have 3 times x minus 2 over 3 plus 2. Remember, when it's written this way, whatever's the closest to the x, you put that function in place of the x in the other. Remember doing this? Yes. Well, what happens to these 3's here when I multiply? They're going to divide out, so your answer will be x minus 2 plus 2, which is x. So far that looks good, because they both should equal x when you put them inside of each other. Now let's go the other way. Let's find g composed of f of x. So you're going to put your f of x function inside of the g function. So that means we're going to evaluate g at 3x plus 2. So right here where there's an x in your g function, you've got to put 3x plus 2 in its spot. So that means I'm going to have here 3x plus 2 minus the 2 that's there, all divided by 3. What happens to those 2's? They subtract out to 0, so you're left with 3x over x, 3x over 3, which divide out and leave you x. So your answer is yes. Those are inverses of each other, because the composite function both equal x. is equal to negative 4x plus 2, and g of x is equal to negative 1/4 x minus 2. Let's see if these are going to be inverses of each other. Kind of looks multiplying by negative 4, dividing by 4, adding 2, subtracting 2. Let's see what happens. Find f composed of g of x. That means you put your g of x function inside of the f function. So right here where there's an x, you're going to put your g of x function, right? So that's going to be negative 4 times negative 1/4 x minus 2 plus 2, right? Put the g function, which is negative 1/4 x minus 2, in place of the x in the f function, right? What happens to my 4's? They'll divide out, and a negative times a negative will give you a positive x. But what's negative 4 times negative 2? Positive 8 plus 2, which gives you x plus 10. Did that equal x? No. So this one, your answer is no. Those are not inverses. If your answer is no, you don't have to find the other one. They both have to be true for it to work.
We get rid of the 4, how do you get that?
Because you got to distribute the 4 all the way through. So you got to
Or
say,
you cancel it out?
well, it canceled out with this term, but you still had another
You
term
Still have, okay.
to distribute it to. Are we okay there?
Is that a negative x plus 8 plus 1?
It's x plus 8 plus 2. Because when you say negative 4 times negative 2, you get a positive 8. Here, let you do one here. Number 3. Number 3, let's say if we have f of x is equal to 3x plus 9, and g of x is equal to 1/3 x minus 3. See if these two are inverses. Calculator give me the answer? The calculator give me the answer? It is not. It's fine. We should be doing number 3, which is on this side. What y'all think? Yes or no? Yes. Let's look and see. So you the first one, you find f composed of g of x, so you put your g of x function in place of the x and the f of x. So that's going to be what? 3 times 1/3 x minus 3 plus 9, right? 3, there's my x, so I'll put the g function plus the 9. Well, 1/3 times 3 would just be x. 3 times -3 would be -9, and then you have your positive 9. Those subtract to 0, and the answer is x, right? Now, this one's got to equal x2 for it to be true. But the f of x function into the g function. So I got to put my f of x function in place of this x. So it's going to be 1/3 times 3x plus 9 minus 3. 1/3 times 3 is x. 1/3 times 9 would be positive 3 minus the 3. You got x again, right? So yes, your answer is yes. Those are inverses of each other. You follow what we're doing? Remember how to do these from your third test? You okay there? Alright, let's look at this other one. This is another good thing about this material because it's going to review you on complex fractions, which we had on test 1. So we want to know where these functions inverses of each other. F of x is 1 over x plus 1. G of x is 1 minus x over x. So let's plug in. Find f composed of g of x. So you're going to put your g function inside of the f function. So right here where there's an x, you've got to put your g function. So that's going to be 1 over 1 minus x over x plus 1, a complex fraction. How do we simplify a complex fraction? Right? You find the common denominator to the little fraction and you multiply it times every term, right? What's the common denominator to that little fraction? X. So you multiply it times every term. Get rid of that little fraction. So in the numerator, 1 times x is x. Here they divide out, so I have 1 minus x. 1 times x is x. Right? What's going to happen to these x's right here? They subtract out to 0, so you're just left with 1. And of course, x over 1 is just x. Right? Now let's see if we can go the other way. Let's find g composed of f of x. So you put your f function into your g function. Well, our g function's got 2 x's. So we'll have to put it in both of those. That's going to be 1 minus 1 over x plus 1 all over 1 over x plus 1. And what's my least common denominator on this complex fraction? X plus 1. So we need to multiply every term by x plus 1. Well, 1 times x plus 1 will give me x plus 1. Here, those divide out, so you're just left with minus 1. Here, your x plus 1's divide out, so you're just left with 1. And of course, you've got your x. 1 minus 1 subtract to 0, so your answer is just x on both of them. So your answer would be yes. Those would be inverses of each other. Any question on these two? We're going to do one more, proving them by the definition, and then we'll learn how to find our own inverse. This next one is actually number 50 in your book. You're told that f of x is equal to the square root of x plus 8. It also has written down here that this domain would be from -8 to infinity. Because remember, this is a square root graph, and you ask yourself what would make that 0, it would be what? -8 would make that 0, right? So that means this graph will come out here at -8 and look like this, right? For your basic graph. And you're also told that g of x on this one is x squared minus 8, but you're told on this one that we want to restrict the domain to be just the positive numbers. Well, basically, this is your parabola, your x squared, but it's got a -8 on the outside of the function, so it would go down 8 But we're only going to take into account where the domain is positive. You don't want the left side of the parabola because like we talked about earlier, it wouldn't be 1 to 1 if you did the whole y, right? So that's why on this problem, it has to restrict the domain. This will be given to you. You don't have to remember to do it on your own. It will be in the problem. Remember we talked about earlier? Square root function is 1 to 1. It passed the vertical and horizontal line test. And the opposite of square rooting something would be squaring. But if I did the whole parabola, it failed the horizontal line test, right? So that's why you have to restrict the domain to only the positive numbers. You with me? Alright. You're not going to be asked this, but I want you to see something that happens here that's neat. Looking at this graph, what would you say the range is? What's the range of all square root graphs? If you take the square root of something, what kind of answer do you always get?
All of them.
Well, can you have a negative under a square root?
No.
No. So what kind of answers do you always have to get? Positive, right? Looking at this picture, what's your smallest y value? 0, and it goes up, right? So on this one, your domain would be from -8 to infinity. Your range is from 0 to infinity, correct? Over here on this one, what would you see the domain is your left to right, your x's, 0 to infinity. What would the range be on this one? What's your bottom y value here? It goes all the way up to infinity. What do you notice about the domain and range of these functions? They swapped, right? And you're going to find that that's something that happens with inverse functions when we find our own. One of the steps is that you swap your x and y's, which swaps out the domain and range. On every inverse function, the domain of one it becomes the range of the other. The range of the first one and the other one it becomes the domain. They always swap places. That's what an inverse function does. That's how they undo each other. And when you do composite functions, you get a plain x. Alright, so let's look. Let's do this composite function and see if these two are inverses. Let's find f composed of g of x. So you're going to put your g function inside of the f function. Well, here's the f function. You've got to put your g in place of that x. So that'll be the square root of x squared minus 8 plus 8, right? Your g function, which is x squared minus 8, goes in place the x in your f function. Right? What happens to my 8's? They subtract to 0, so I get the square root of x squared. What is the square root of x squared? X. Remember, you divide your root into the exponent. 2 goes into 2 one time, so 1x comes out. Now let's do it the other way. G composed of f of x. You put your f function inside of your g function. Well, my g function is x squared, so that means I'm going to have the square root of x plus 8 squared minus 8. Because my g function is x squared minus 8. Wherever there's an x, you got to put the square root of x plus 8, square it, minus 8. What happens when you square a square root? What do you get? What's underneath? Good. So that gives me x plus 8 minus 8, which is equal to x. So yes, those two functions are inverses of each other. Are we good there? Yes, no? Good. Now we're going to talk about how you can find the inverse. Let's say if you're, we're going to do steps to find the inverse function. And the notation for the inverse function looks like you got an exponent as a -1, but it's your function notation with a little -1 written there of x. That's the notation for the inverse function. Step 1 is you're going to make sure f of x is a 1-to-1 function. If f of x is not 1-to-1, then it will not have an inverse. So make sure f of x is a 1-to-1 function. Then you're going to swap your x and y. And the reason we swap the x and y is because on our inverse function, your domains and range swap. That's what we just saw that takes place here. So step 2, you must swap x and y. Step 3, you will solve for y. And as you're solving for y, to get it on the side by itself, you have to do the opposite of each of those operations to get y by itself. And step 4, you will replace y with the inverse notation. Now on your test, you'll have to prove one by the definition, and then you'll have to find the inverse. Now I always have somebody that tries to be real slick, and if I give you one, they just go through these 4 steps and say, yes, it's the inverse when I went through the steps, so it works. But you will have to actually prove by the definition and do this composite function there. Okay? So let's see if we can do our steps. So your directions are to find the inverse, which is, so for number 1, let's say if I have f of x is equal to 3x minus 5. Well, what is f of x the same thing as? Same thing as y, it's just function notation. So what I have here, if it's written in function notation, means it's really the same thing as y equals 3x minus 5. Those are equivalent, they're exactly the same thing. Well, ask yourself, is this a one-to-one function? Yes, no even exponents, no absolute values. So step 1's taken care of. Now step 2, we got to swap x and y. Swapping out that domain and range. So this will be x is equal to 3y minus 5. We swapped x and y. Now we're going to solve for y. Well, what do I need to do first to get y by itself? You need to add 5. You're doing the opposite, right? So this will be x plus 5 is equal to 3y. Now what do we need to do to get y by itself? Divide by 3. So I get x plus 5 over 3 is equal to y. Step 4 says you just replace y with the inverse notation, and you're done. People use it like this better than the definition part. And you can check them. You can let this be f of x, this be g of x, and go through that definition and prove that they both equal to x.
So that -1 is the top domain?
No, that's just a notation. Okay? Alright, let's look at another one. Number 2.
The part you got started on there is step 4.
Yes, that's when you replace y with f inverse, yes. Alright, this time let's say we have y is equal to 2 over x plus 5. Well, is this one-to-one?
Yeah.
Do you have any even exponents in your absolute values? No, so it is one-to-one, which means that it does have an inverse. Now we need to swap our x and y. So I'm going to have x is equal to 2 over y plus 5. Well, I've got an equation that involves a fraction. Anytime you have any equations with fractions in them, what did you always do? Anytime we've seen a fraction, what have we always done to get rid of it? Multiply by the least common denominator. What is my least common denominator? Y plus 5. So let's multiply both sides by y plus 5. We're solving for y. So here, let's do our distributive property. X times y would be xy. X times 5 is 5x. There, they divide out, so you're just left with the 2.
You couldn't just like multiply 2 by both sides?
Well, that wouldn't help you, because over here you'd still have 2 times 2 and give you a 4 in the top. You want to get that y out of the denominator so you can solve for it. Okay? Is everybody okay so far on what we've done? Multiply both sides by the denominator. And then I distributed the x. Now we want to get this y by itself. I need to move over and get rid of? 5x. So I need to subtract 5x from both sides, right? So I'll get xy is equal to 2 minus 5x. Now what do I need to do to get y by itself? Divide both sides by x. So you end up with y is equal to 2 minus 5x over x. So for your fourth step, replace y with f inverse. So f inverse of x is equal to 2 minus 5x over x.
So you always put the -1 by the x?
Yes, that's the notation for the inverse, so yes, you'll always do that. Okay, let's look at another one, number 3. Let's say if I have y is equal to x cubed plus 2. Well, see if you can do this one on your own. I'll give you a minute. Got it? Alright, what is this one 1 to 1? Yes, no even exponents, no absolute values. So we're going to swap x and y. So I'm going to have x is equal to y cubed plus 2. Now let's solve for y. What do I need to do first to get y by itself? So I get y minus 2 is equal to x cubed. What's the opposite of taking the cube root of something? What can I do to both sides? I said wrong. What do I do to get rid of a y cubed? You take the cube root of both sides, right? So I get here that the cube root of x minus 2 is equal to y. So that means that I have the cube root of x minus 2 is equal to f inverse. Which makes sense. The opposite of cubing something would be taking the cube root. The opposite of adding would be subtracting by 2, right? Let's say if you are on your test and you have found the inverse and you do want to check it by using what we were doing earlier. If you want to check it, like they say f of x is your original x cubed plus 2, and then let's say g of x is the cube root of x minus 2. Your original function and the inverse that you found. Well, if you got it right when you do the composite function, they'll both equal x. So let's find f composed of g of x, which means we put the g function inside of the f. So that means I'm going to say the cube root of x minus 2 cubed plus 2. What happens when you cube a cube root? You just get what's underneath. So that will give you x minus 2 plus 2, which is just x. So far it's looking good, like you did it right. Now you want to find g composed of f of x. So you're going to put your f function inside of your g function. So it's going to be the cube root of x cubed plus 2 minus 2. right? My 2 subtract out, so I'm just left with the cube root of x cubed. 3, you divide the root into the exponent. 3 goes into 3 one time, so an x comes out. So yes, you did that problem correctly, and you checked it. Now, like I said, this is just the checking it.
We will have to check it.
No, that's just if you want to.
Oh,
Why would you want
To make sure you got it right.
it's gonna take me long enough to do the.
And I'll tell you this, the reason I showed you is, I haven't decided how I'm gonna do it, but if you have a written test, sometimes I make you find the inverse, and then I'll tell you to check it, so you know you got it right, instead of actually doing like what we did earlier, proving that they were inverses of each other. So I can give you one problem that'll cover the definition and the steps to find the inverse. And you know if you miss that you miss this, and you go back and get them both right. Right? Alright, that's section 4.1. That's the inverse function. Now we're going to start section 4.2. Exponentials. And y'all going to like this. This is kind of, once we solve exponential equations, it's kind of like playing the game. Section 4.2, exponential function. Exponential function. So this is like if you have y is equal to a to the x power. So what's going to happen on this exponential function, the way it's going to be different than all the other things you've seen with exponents, is because your unknown is going to be the exponent. Right, Macy? So this time our x is my unknown. A is going to be the base, which is going to be some number greater than 0, but it can't equal 1. And then the x, which of course is your exponent, is going to be your variable, your unknown. Why is it important to say that a cannot, you don't want your base to be 1? What's 1 squared? What's 1 cubed? 1 to any power stays 1. So that's the reason we don't want our base to be 1, because then it's just that horizontal line, y equal 1, which doesn't help us. So we want our base to be some number greater than 0. We don't want it to be 0, because 0 to any power stays 0. And then you have certain properties that hold true if this works. If x is any real number, then whenever you put in a number up there, if a is a base, you're going to get a unique number. Like if, let's see if we had y is equal to 3 to the x. Well, if I put in 1, what am I going to get? 3. If I put in 2, what am I going to get? 9. So any number you put in for x, as long as a is greater than 0 and not equal to 1, you're going to get a unique real number answer. You can always put in and get answers there. One property that's real important to us when we're doing these, this is going to help us when we start to solve them. Well, let's just do this. Is if you're told for one of your properties that if you have a to the b power is equal to a to the c power, if your bases are the same, what is the x, and you've got something equal, then what's the exponents? They have to be equal too, right? Like if you had 3 to the x is equal to 3 to the y, doesn't that mean that x and y have to be equal to make that a true statement? Because only 3 squared is only equal to 3 squared, and so forth, right? So your big property that we're going to use a lot is anytime your bases are equal, if the bases are equal, then the exponents must be equal. Or vice versa, if the exponents are equal, then the bases have to be equal. We're going to use that a lot when we start solving these exponential equations. But first, we're going to make sure you know how to graph one. Alright, let's say we're going to graph. We'll do this y equal 3x. And also, this is a function, you'll see them when we graph it, that it will pass the vertical line test. So it could be written as f of x equals 3x as well. So let's say if it's written in function notation, if we want to do a t-chart here to graph. let's say we want to find, well, let's do function notation. We'll graph it in a second. Number one, we want to find f of negative 1. Number 2, f of 0. Number 3, f of 1. 4, we want to find f of 2. So let's set,
We're given f of x is 3.
we're given f of x equal 3x, and then we want to find f is equal to 3 halves. See if we can find these. Alright, well how would I find f of negative 1? When it's in function notation, what's your rule? What do you do?
The number with the
Right.
function.
Whatever's in the parentheses, put it in place of the x, right? So this will be 3 to the negative 1 power. Well, what do I have to do to make that exponent positive? Take it to the bottom. So that means this will be equal to 1/3. Right? F of 0. What would what's anything to the 0 power equal to? 1. So 3 to the 0 would be equal to 1. F of 1 would be 3 to the first power, which equals 3. F of 2 would be 3 squared, which equals 9. Now let's do this 3 halves. That's going to be 3 to the 3 halves power, right? Well, do you remember how to write a rational exponent as a radical?
Something like the square root or something. Or you
Right. Whatever's in the denominator is the root. Remember, roots come from the ground. The power's in the top. So this would be the square root of 3 cubed, or the square root of 27. Can you simplify that?
3
3 on the square root of 3.
Right. Because 27 would be 9 times 3. The square root of 9 is 3. So that's 3 square root of 3. Y'all are good. Alright? So that's how you can evaluate it in function notation. Now let's talk about if we want to graph it, and I'm going to do the T-chart, which is what I started to do first.
This is function notation.
Alright? So if you're told to graph, let's say y equals 3x, and you're given your T-chart, we're going to do -1, 0, and 1. Which we've already found because we just did function notation. Right?
So which way is it?
Well, it just depends on how I ask you on the test. Your book's going to ask you both ways, so that's why I'm doing it both ways. Alright, so f of -1, that's going to be 3 to the -1, which is 1/3, right? Put a 0 in place of the x. That's 3 to the 0, which equals 1. 3 to the first power equals 3. With me there? So when I go to graph these and plot these points, I've got the point -1, 1/3. I've got the point 0, 1, and the point 1, 3. This is what this graph will look like. Now, one thing I want to say about this graph is, do you agree that there's not any number I can put in there for x that would ever make this problem give me a negative number? If I put in 3 to the -10 power, that would be 1/3 to the 10th, right? Which would be some huge number. If I put in, -6, that's going to be 1/3 to the 6th, which would be some, 3 to the 6th would be some real big number, which would be a real tiny fraction, right? You with me there? So this graph here, this is called an horizontal asymptote, which you don't know the terminology, but it'll never cross the x-axis. It'll get real close. The more negative that x gets, it'll get closer and closer to 0, but it'll never actually equal 0. The only way you'd ever get 0 would be if your base is 0, and we already said x, their base is always going to be greater than 0. Okay? Now let's look at another one. Let's say if I want to graph y. Go ahead.
Um,
No, ask.
I was gonna ask how you know the curves, but it's because it's
I know what? When it curves, because I plotted the points. Okay. All right, let's say if we want to graph y equals 1/3 to the x. Can we do our same t-chart here? -1, 0, and 1. We're going to see how this graph is going to look different, a little bit different from the other one. Before you start plugging these numbers in, let's jump ahead of the game. What did you tell me earlier? What is anything to the 0 power equal to? 1. It doesn't matter what your base is. If it's raised to the 0 power, it always equals 1. So that means on every one of these exponential graphs, they're always going to go through the point 0, 1. Every single time they're going to go through that point. Well, let's put in -1 in place of that x. So that would be 1/3 to the -1 power. What did you just tell me? How do I make that exponent positive? By doing what? By flipping it. So that means that will be equal to +3, right? And down here, if I had 1/3 to the first power, what's that going to be equal to? 1/3. So let's graph this one. At -1, I'm at 3, so I've got the point -1, 3, the point 0, 1, and 1, 1/3. And that would be your graph. What do you notice looking at these graphs? What do you see is the difference?
Opposite side.
One of them, this one you would say is what? Increasing? Going up? What's this one doing? Decreasing. And that's the way it's going to look every time. If your base is a whole number, your graph will be increasing. If your base is a fraction, your graph will be decreasing. Every single time. And you can always do your t-chart to figure them out. But they'll always go through the point, every exponential function goes through the point 0, 1. And then you can always get these. If it's the whole number, you know, you flip it, you get that fraction, that little number. When you put in 1, you get 3. So you can almost just plot the 0, 1 and put in 1 and know the shape and get this graph, right? No matter what the numbers were. You with me there? Maybe, yes? Alright, now let's talk about solving some of these exponential equations. We'll get to the fun stuff. So if you're told to solve an exponential equation, that property that I just told you a few minutes ago, about if the bases are equal, then the exponents have to be equal. We're going to use this the whole time to solve an exponential equation. Remember we said if you have a to the b power is equal to a to the c power, then b has to be equal to c. If the bases are equal, then the exponents must be equal. So the way you're going to solve an exponential equation, the whole key is that you're going to rewrite the bases so they are the same number. Then set the exponents equal. So your whole key is going to be you rewrite the bases so that they're exactly the same number. And when they are, then you can set the exponents equal to each other and solve these equations. This is really neat. Y'all gonna like this.
You said it.
Every time.
Yeah.
Now I really thought did y'all not agree that last test, that bonus, that was a neat problem that you could solve that whole problem. I mean, when if I put that problem on the board the first day of class and showed it to you and said, we're gonna learn to solve this whole problem, you would have never believed.
I would have said neat.
But that's neat the way it works out, that you can do it that way.
You
It's
think
cool.
math is neat, that's how your brain works, but mine doesn't work like that. So.
But even, aren't you proud of yourself that you can do that humongous problem?
Yeah.
Yeah.
I mean, once you do it, you're like,
I'm very disappointed in myself.
alright, okay. Alright, so let's look at these. Let's solve these equations. Number 1. If I have 3 to the x is equal to 9. Now these first one you're going to be able to look at and you're going to be able to tell me what x equals because it's going to be obvious. But I'm going to show you on some of these obvious ones so you'll know how to do the harder ones. Okay. Well, you're going to ask yourself, can I write 9 with a base of 3? Is 9 3 to any certain power? 9 is the same thing as what?
3 is the same.
3 squared. So here I can say that 3 to the x is equal to 3 squared. And based on that properties, if my bases are equal, then that means my exponents are equal. So for this problem, x has to equal 2. And then look what you can check it. What's 3 squared? 9. And like I say, that one you can tell by looking. You know what would x have to be to get 9 for your answer? 2. But the key is you're going to rewrite it to where your bases are the same number. Okay? Let's look at another one, number 2. Let's say if I have 2 to the x plus 4 power is equal to 8. Well, can you write 8 with a base of 2? Can 8 be rewritten as 2 to some power? What's 2 cubed?
Yeah. 8.
8. So we're going to rewrite 8 with a base of 2. So we'll have 2 to the x plus 4 power is equal to 2 cubed. Because 2 cubed is the same thing as 8. Did I ever give you all those little cards that had all the powers on
Yes,
them?
ma'am.
Remember those? Cool. We'll get you another one. Because you might want to look at that and get used to using it on this stuff. Y'all remember what I'm talking about? We had all the list of squares, list of cubes.
Yes.
Yeah, a little blue sheet. Alright, so now that my bases are equal, I can set my exponents equal. So that means x plus 4 has to equal 3. What do I need to do to solve for x? Subtract 4 from both sides. So x is negative 1. Well, check it. What's negative 1 plus 4? 3. What's 2 cubed equal to? 8. Isn't that neat the way that works, too? Alright, let's look at another one. I'm going to give you a little different one here. Number 3. Let's say if I have 9 to the x plus 1 is equal to 27 to the x power. Got a little harder all of a sudden. But think, you can't write 27 as 9 to a power.
3 to the third.
What? Go, John. Yeah, you can rewrite both of those as 3 with a base of 3, right? I can write 9 as what? 3 squared to the x plus 1 power, and 27 would be 3 cubed to the x power, right? 9 is the same thing as 3 squared. 27 is the same thing as 3 cubed, right? Now, what's my rule here for when there's an exponent on the outside of the parentheses? What do you do with them? You multiply them. Remember, if there's exponents on the outside of the parentheses, you multiply them together. So I actually have here 3 to the 2x plus 2 is equal to 3 to the 3x power. Now, if my bases are equal, what can I do with my exponents? Let them equal. So I get 2x plus 2 is equal to 3x. What do I need to do to solve for x? Subtract 2x from both sides. So I get 2x is equal to 2. And look up here. If I put a 2, if you can check them on your calculator, you can say 9 cubed, write that answer down, and then say 27 squared, and you should get the same answer. You follow me there? Let's look at one more here where you got some fractions. Number 4. We have 1/2 to the 3x minus 6 power is equal to 8 to the x plus 1. Okay. Anytime you see a fraction, rewrite it with a negative exponent. Okay? Do you agree 8 is 2 to some power, and you can write 1/2 as 2 to the negative 1. So anytime you see a fraction, this is going to be your worst case scenario, but if you remember this, it'll help you. Anytime you got a fraction, rewrite it with a negative exponent. So this 1/2 I'm going to write as 2 to the negative 1, and that's to the 3x minus 6 power. 8 I can write as 2 cubed, and that's to the x plus 1 power. Okay? Everybody okay there? You know where that 2 to the negative 1 come from? Remember, if you have a negative exponent, you flip it. So anytime you have like 1/2, you can write as 2 to the negative 1 instead. Y'all, you with me there? Now, this would be 2 to the negative 3x plus 6, when you distribute that negative 1, is equal to 2 to the 3x plus 3. Using that distributive property, multiplying exponents. Now that your bases are equal, you can set your exponents equal. So negative 3x plus 6 is equal to 3x plus 3. Now we want to solve for x. So get your x's on the side together. Let's say we add 3x to both sides. That gives me 6 is equal to 6x plus 3. Subtract 3 from both sides. So I get 3 is equal to 6x. Divide both sides by 6. So you get x is equal to 1/2. A lot of people want these 3's to cancel out, but notice their signs are different. So when you combine them, if I add this 3 to this side, 3 plus 3 gives you 6. Okay? Let me give you some homework problems out of this section, then we're going to talk a little bit more for just a second.